Today we're going to be solving problem number 49 from chapter 3. The problem reads, a rocket is launched at an angle of 53 degrees above the horizontal with an initial speed of 100 meters per second. The rocket moves for 3 seconds along its initial line of motion with an acceleration of 30 meters per second squared. At this time, its engine fails and the rocket proceeds to move as a projectile. Find A, the maximum altitude reached by the rocket, and B, the most total flight, and C, its horizontal range. So for part A, we're going to first be using velocity final equals velocity initial plus A delta t to find the final velocity of the initial line of motion. So we would plug in the appropriate values, and we get velocity final as 190 meters per second. And now we're going to do some trigonometry to solve for the x and y components of its initial line of motion. We know this is a right triangle with a 53 degree, and it's 100 meters per second for the velocity initial there. So we'll use sine 53 equals y, if we're going to put this as y, over 100 meters per second. So that means y would be equivalent to 79.9 meters per second. Okay, so with that information, we would plug it into delta x equals velocity initial t plus 1/2 at squared. So delta x equals 79.9 meters per second times t, which is still 3 seconds, as it stays consistent through the x and y, and plus 1/2 minus 9.8 meters per second squared times 3 seconds squared. So delta x, when simplified, would equal 95.6. Now we're going to do a chart for the new x and y components. So velocity initial, readjust it a little bit. Velocity initial, velocity final, acceleration, delta x and t. So it's velocity initial. We don't know anything for the x except that acceleration is going to be 0 meters per second. So velocity initial will be equivalent to velocity final. We're solving for its highest point. So what we're going to do is we're going to make another graph and reset. And for this part, we're going to have point 0 as here after it becomes projectile and it starts going downward. We know its initial velocity would be 190 meters per second. It would be at a 53 degree angle as it stays in the consistent line of motion, so the angle would carry on. And then we know the height would be 195.6 meters. So from there we would also use trig to solve for its x and y components. So if this is 190 meters per second, and this is at a 53 degree angle, and this is a right triangle, it'd be sine 53 degrees is equivalent to y over 190 meters per second. So now we know y is equivalent to 151.7. So we have its initial velocity. And we know we're solving for the maximum height. And when it reaches its maximum height, it has a velocity of 0 meters per second. So we know its velocity final would be equivalent to 0 meters per second. So with that information, we also are going to solve for the velocity initial of with this. So it would be cosine 53 equals, and we'll put this as x over 190 meters per second, and that would be equivalent to 114.3 meters per second. So now we know the velocity initial, and because it has an acceleration of 0, we can also say that the velocity final is also 114.3 meters per second. As well, we know the acceleration for y would be minus 9.8 meters per second squared. Now, with that information, we're going to go back here. We're going to plug it into velocity final equals velocity initial plus a delta t to solve for the time it takes to reach its max height. So it would be 0 meters per second, and this is for the y component, 151.7 meters per second plus minus 9.8 meters per second squared times t. And then when you solve for t, you would get a value of 15.5 seconds. Now, with that, we're going to plug into the equation delta x equals velocity initial t plus 1/2 at squared. So we would substitute in for our variables. So it'd be 151.7 meters per second times 15.5 seconds plus 1/2 9.8 meters per second squared times 15, it'd be negative 15.5 seconds squared, and then delta x would be equivalent to 1174.1 meters. Now, with that information, we can solve for the max height. So we know that in the graph here, that it traveled up the 1174.1 meters, and then it would also be plus the 195.6 meters. So the maximum height equals 1,369.7 meters. And that's our solution for part A. It may be a little bit off due to rounding, but it should be somewhere relatively close to that. Now for parts B and C, it's a bit simpler because now we did most of the work. So we're going to also break it down into our x and y components with a new graph. It's going to be slightly different because instead of solving for the maximum height, we're going to solve for B, which is its total time of flight. So I'm going to set the velocity initial, velocity final, acceleration, delta x, and t. So 114.3 meters per second, as it will stay consistent, and then 114.3 meters per second. So that part carries on, and then 0 meters per second. And then we have the velocity initial of 151.7 meters per second. But this time we do not know the velocity final, as it's not 0, as we're not solving for maximum height. However, we do know the acceleration, which is minus 9.8 meters per second. Now from there, we're going to try to solve for, and what we're gonna do as well is to actually have a third component for this. We're going to solve delta x as minus 195.6 meters. This is because I'm setting this part as 0, this way is positive, and this way is positive. So once it goes past its initial curve in which it reaches the same delta x for the y component, I say we're going to make it go into the negative, so we can actually have a third component because we're trying to reach for how long will it take after that curve to get all the way back down the 195.6. So now we're going to plug in our values of delta x equals velocity initial t plus 1/2 at squared. So that'd be minus 195.6 meters equals 151.7 meters per second times t plus 1/2 minus 9.8 meters per second squared, t squared. So basically, at that point, we would use quadratic to solve for the two values that are given. So I would put in a quadratic equation. So minus 4.9 meters per second squared, t squared, plus 151.7 meters per second times t plus 195.6 meters. And then you can plug that into your calculator to solve for a graph. And then if you solve for the zeros, you would get minus 1.2 seconds, or t equals 32.2 seconds. So we can find out which one of these is the actual one, and it has to be the 32.2, as you can't have a negative value for time, so this would not work. So now that we know the time it took for it to go from here all the way down, we would add the 3 seconds of its initial line of motion. So 32.2 seconds plus 3 seconds equals our answer for B, which is 35.2 seconds. So that's our answer for B. And now for C, it's quite simple. All we have to do is we'll go back to our initial triangle where we had the 114.3 meters per second. Solve for our first part, because right now we're solving for the entire horizontal range, so we have to consider the first and second part. However, because in the horizontal and vertical range, it stays consistent of 114.3 meters per second, we can solve for it quite easily. So delta x equals 1/2 velocity initial plus velocity final t. So now that because velocity initial and velocity final are the same and divided by 2, we can just substitute it for delta x equals 114.3 meters per second times 35.2, which is its entire motion. So delta x would equal 4,023.36 meters. So that's its entire. That's our answer for part C. Its entire horizontal range. So yeah, that's the answer for problem 49. If the answers are slightly off, that's most likely due to rounding, as I rounded usually just the 10th place. So that would most likely be the reason for that. Okay, thank you.